Imagine a computer, not just any computer, one that doesn't just calculate, it possibilities simultaneously, a machine that could unlock the universe's deepest secrets. This isn't science fiction, this is the promise of quantum computers. We stand at the edge of a new computational revolution, a revolution powered by the strange, wonderful rules of the quantum realm. The universe itself, it operates on quantum principles. So, why shouldn't our most powerful tools tap into that same cosmic power? This new frontier beckons us, it calls to our innate human curiosity, that deep-seated desire to understand, to build, to solve the unsolvable. Quantum computers are far more than just faster calculators. They represent a fundamental, thrilling shift in how we approach complex problems. They offer an entirely new lens. A lens through which to view the intricate tapestry of reality, from the dance of the tiniest subatomic particles, to the grand, sweeping evolution of the cosmos itself. These machines could truly redefine what humanity deems possible. Think about the grand challenges. The big ones: climate change, threatening our planet, incurable diseases, touching so many lives, the deep, dark mysteries of dark matter and dark energy. Our trusty classical computers, for all their incredible power, sometimes hit a wall. They simulate, they model, but some problems are just too vast, too complex. Quantum computers offer a new path, a way to tackle these monumental tasks with a completely different kind of intelligence. An intelligence that mirrors the universe's own elegant quantum processes. So, prepare to have your mind expanded. Gently, of course, we're about to embark on a journey into a world where particles can be in multiple places at once. Yes, really, where they can be mysteriously linked instantly, no matter the distance separating them. This is the world of quantum mechanics, and it's this very world that gives quantum computers their extraordinary, almost magical power. Fasten your cosmic seatbelts. The future of computation is not just arriving, it's already knocking, inviting us to step through into a new age of discovery. So, what exactly a quantum computer? Let's try to unravel this. Imagine a regular computer, the kind you use every day. It thinks in bits, zeros and ones, on or off. Simple, clear, like a light switch. It's either on, illuminating a 1, or it's off, resting in 0. This binary system, this language of two, has served us incredibly well. It's the solid bedrock of our entire digital age, from your smartphone in your pocket, to the giant supercomputers predicting our weather, all built on this elegant simplicity. Now let's enter the quantum realm. Quantum computers don't just use plain old bits, they use something far more exotic, something called qubits, quantum bits. And here's where our everyday intuition takes a vacation. A qubit isn't just a 0 or 1, it can be a 0, it can be a 1, or it can be. Amazing, isn't it? This both at once property has a name: superposition. Think of a spinning coin. While it's twirling in the air, it's neither heads nor tails, it's in a superposition of both states. Only when it lands, when does it choose one. This remarkable ability to exist in multiple states simultaneously is a complete game changer. It means a quantum computer can explore a truly vast number of possibilities all at once. A classical computer must check each path, one by one, methodically. Imagine trying to find your way through an enormous complex maze. You'd have to try every single turn sequentially. A quantum computer, however, can, in a way, explore all possible paths of that maze at the very same instant. This isn't sorcery. It's the fundamental nature of reality at its smallest, most mysterious scales. Therefore, a quantum computer isn't merely a faster version of the familiar computer on your desk or lap. It's a completely different kind of thinking machine. It directly harnesses the peculiar laws of quantum mechanics, the very laws that govern atoms, electrons, and photons. It operates in a domain where the everyday rules of classical physics gently give way. Or rather, where a deeper, more fundamental, and frankly more wondrous set of rules comes into play. The very idea of quantum computing isn't brand new. It didn't just suddenly appear out of thin air yesterday. Its conceptual roots stretch back decades, all the way to the early revolutionary days of the 20th century, when brilliant physicists like Max Planck, Albert Einstein, Niels Bohr, and Erwin Schrödinger were first wrestling with the utterly bizarre nature of the quantum world. They laid the crucial theoretical groundwork. They discovered that energy wasn't continuous but came in discrete packets called quanta, that particles could act like waves, and waves like particles. This was the dawn of quantum mechanics. Let's fast forward to the 1980s. A physicist named Paul Benioff took a significant step. He first proposed a quantum mechanical model of a Turing machine. This was a theoretical construct, a computer that, in principle, obeyed the strange laws of quantum physics. Then, the legendary Richard Feynman, a Nobel laureate with a famously curious mind, made a keen observation. He realized that trying to simulate quantum systems on classical computers was incredibly, profoundly difficult. So, he pondered, why not build a computer that operates on quantum principles? A quantum simulator. This was a pivotal moment. Another key figure in this unfolding story is David Deutsch. In 1985, he described a universal quantum computer. He showed that such a machine could, theoretically, perform any computation that a classical Turing machine could, and, crucially, much more. He also developed the very first quantum algorithm, known as Deutsch's algorithm. It elegantly demonstrated, albeit for a relatively simple problem, that a quantum computer could indeed be faster than any conceivable classical counterpart. The focus was shifting, from mere simulation to true quantum computation. The race, a marathon, not a sprint, had quietly begun. Since those foundational insights, progress has been steady, if undeniably challenging. Physicists and engineers across the globe have experimented tirelessly. They've explored various ways to build and control these elusive qubits. Trapped ions, superconducting circuits, photons, even tiny imperfections in diamonds. Each approach comes with its own unique set of advantages and difficult hurdles. We've seen the exciting development of new quantum algorithms, like Peter Shor's algorithm for factoring large numbers, a big deal for modern cryptography. And Love Grover's algorithm for searching unsorted databases. It's been a journey of brilliance, patience, and relentless quantum pursuit. We've touched upon bits and qubits, but let's delve a little deeper. What truly separates our familiar classical computers from their exotic quantum cousins? The fundamental unit of information is the absolute key. Your laptop, your smartphone, they all speak the language of bits. Each bit is a clear, unambiguous 0 or 1. Think of it, once more, as that simple light switch. It's either decidedly off, representing a 0, or it's definitely on, representing a 1. There's no confusing in-between state. This binary system is wonderfully deterministic. Give a classical computer the same input, you'll always get the same output. Quantum computers, however, operate in a much fuzzier, more fascinating world. A world of probabilities and superpositions. Their qubits, as we've learned, are not just simple zeros or ones. They can be a delicate combination of both, thanks to that marvel of superposition. Imagine, instead of a flick switch, a dimmer switch for a light. It can be fully off, 0, fully on, 1, or any subtle shade of brightness in between. A single qubit, therefore, can hold vastly more information than a single classical bit. 2 qubits? They can represent 4 states simultaneously. 3 qubits? 8 states. The number of accessible states grows exponentially. This exponential scaling is precisely where the almost unbelievable power of quantum computers lies. A classical computer with, say, 64 bits can store and process one single value out of 2 to the power of 64 possible values at any given time. A quantum computer equipped with 64 perfect qubits can, in a very real sense, store and process 2 to the power of 64 values simultaneously. Now, this doesn't mean it magically spits out all those answers at once. The true artistry lies in designing clever quantum algorithms. Algorithms that skillfully use this massive parallelism to find the specific answer you're looking for, far faster than any classical computer ever could for certain problems. Another crucial difference is how these two types of computers handle errors. Classical computers have very robust, well-developed error correction mechanisms. Bits can occasionally flip due to electrical noise or radiation, but we have ingenious ways to detect and fix these blips. Qubits, on the other hand, are incredibly fragile. They are exquisitely sensitive to their environment. The slightest disturbance, a tiny vibration, a stray electromagnetic field, can cause them to lose their precious quantum state. This is called decoherence. Maintaining quantum coherence long enough to perform complex calculations is a monumental engineering challenge, a true test of our ingenuity. Section 5. The magic inside superposition and entanglement explained. Let's talk more about the quantum magic itself, the phenomena that truly power these extraordinary machines, superposition and entanglement. We've already met superposition. It's that remarkable ability of a qubit to exist in multiple states at the very same time. Like that spinning coin, simultaneously heads and tails until the moment we look, until we measure it. This property allows quantum computers to explore a vast landscape of possibilities in parallel. Instead of ploddingly checking one route after another in a colossal maze, it's like sending out countless ghostly copies of yourself to investigate all routes simultaneously. This massive parallelism is a cornerstone of quantum speed. But there's another quantum phenomenon, one that is, if possible, even stranger. Even more spooky, as Albert Einstein famously described it. This phenomenon is called entanglement. Imagine you have two qubits. You can link them together in a special, intimate quantum way. They become entangled. Once these two qubits are entangled, they are no longer independent entities. They share the same quantum fate, the same existence in a profound way. If you measure the state of one of these entangled qubits, you instantly know the state of the other, no matter how far apart they are. Miles. Light years. It makes no difference. Einstein, a titan of physics, was famously uneasy about this. He called it spooky action at a distance. It seemed to violate the cosmic speed limit, the speed of light, yet experiment after experiment has confirmed it. Entanglement is very real, and it's incredibly useful, indeed essential, for quantum computing. It allows qubits to coordinate their actions in ways that classical bits simply cannot. It helps create complex, multi-qubit quantum states that are absolutely essential for running powerful quantum algorithms. It's like having a team of explorers in our cosmic maze who are perfectly, instantaneously coordinated, sharing information about their paths without a whisper. So, superposition gives you many states at once. A quantum computer can explore many possibilities simultaneously. Entanglement then links these states, these possibilities, together in intricate, powerful ways. Together, these two quintessential quantum effects provide the raw, potent materials for quantum computation. They allow quantum computers to perform types of calculations that are far, far beyond the reach of any conceivable classical computer, no matter how powerful it might become. Section 6. Unleashing the power, the astonishing benefits of quantum speed. So these quantum machines with their quirky qubits, their superposition, their entanglement, what can they actually do for us? What are the tangible benefits? The most frequently talked about advantage is speed. Unbelievable, mind-boggling speed. For certain specific classes of problems, quantum computers promise an exponential speed-up over their classical counterparts. We're not just talking about being twice as fast or 100 times faster, we are talking about tasks that would take the most powerful classical supercomputer billions of years to solve, potentially being cracked by a quantum computer in mere minutes or perhaps hours. This is a quantum leap in every sense of the phrase. Consider, for example, drug discovery and development. The process of finding a new medicine is incredibly complex. It's a chemical labyrinth. Scientists need to simulate how different molecules interact with specific proteins in the human body. There are countless possible molecular combinations to test. Classical computers can model some of these interactions, but they often struggle with the sheer scale and, crucially, the inherently quantum nature of molecular behavior. A quantum computer, because it operates on quantum principles itself, could simulate these vital molecular interactions with far greater accuracy and at much higher speeds. This could revolutionize medicine. Then think about materials science. We constantly strive to create new materials with specific desirable properties. Materials that are stronger, lighter, better conductors of electricity, or more efficient at capturing solar energy. Designing these advanced materials from first principles, predicting their properties based purely on their atomic structure, is another monumental task that often overwhelms even the mightiest classical computers. Quantum computers could accurately model the quantum behavior of electrons within these materials. This could lead to breakthroughs like room temperature superconductors, transforming energy transmission, or new catalysts, making industrial processes cleaner and more efficient. And then there's the intricate world of finance, optimizing vast investment portfolios to maximize returns while minimizing risk, accurately pricing complex financial derivatives, managing systemic risk across interconnected markets. These are all computationally intensive problems that push classical algorithms to their limits. Quantum algorithms, specifically designed for optimization, could find optimal solutions much faster than currently possible. This could lead to more efficient global markets, more robust financial strategies, and perhaps even a more stable global economy. The potential applications for this sheer computational horsepower are truly vast, touching almost every sphere of human endeavor. Section 7. Beyond raw speed, new realms of quantum discovery. While incredible speed for specific, complex problems is certainly a headline-grabbing feature, the true benefits of quantum computing extend far beyond just doing things faster. These machines open up entirely new avenues for discovery and innovation. They allow us to ask fundamentally different kinds of questions, to explore complexity in a way that more closely mirrors nature itself. It's not solely about acceleration, it's about embracing a new paradigm of computation altogether. A deeper understanding of the universe has always been a powerful precursor to transformative technologies, and quantum computers beautifully embody this very principle. Consider the rapidly evolving field of artificial intelligence and machine learning. Quantum machine learning algorithms, still in their nascent stages, could potentially process and analyze data in profoundly novel ways. They might be able to identify subtle patterns in enormous high-dimensional datasets that are effectively invisible to even the most advanced classical algorithms. This could lead to more powerful, more nuanced AI capable of solving even more complex problems, significantly improving medical diagnoses, or perhaps creating more sophisticated and reliable climate models. The synergy between the quantum realm's ability to navigate vast possibility spaces and AI's quest for learning is truly exciting. Cryptography, the vital science of secure communication, is another area poised for a significant quantum shakeup. As we've briefly mentioned, Shor's algorithm, a famous quantum algorithm, possesses the theoretical capability to break many of the encryption methods currently used to protect our sensitive data online. This presents a double-edged sword. While it certainly poses a future threat to existing digital security, quantum mechanics itself also offers powerful solutions. Quantum cryptography, employing principles like quantum key distribution, can create theoretically unbreakable encryption methods. So, quantum computers are both potential codebreakers and essential codemakers for a new era of information security. Perhaps one of the most profound and far-reaching benefits will be in fundamental science itself. Quantum computers are, at their very core, controllable quantum systems. As such, they can be used to simulate other, less controllable quantum systems with unprecedented accuracy and detail. This means physicists could explore the intricate behavior of subatomic particles under extreme conditions, the mysterious nature of black holes, or even the fiery, energetic conditions of the very early universe in ways never before possible. It's like having a perfectly tunable quantum laboratory at our fingertips. This could lead to revolutionary breakthroughs in our understanding of the fundamental laws of nature. Section 8. The Quantum Gauntlet. Navigating the challenges ahead. Now, it's truly important to keep our feet firmly on the ground, or perhaps more aptly, to keep our quantum states coherent and stable. Building practical, large-scale, fault-tolerant quantum computers is an immense, multifaceted challenge. We are still in the very early days of this grand endeavor. Think of it like the dawn of classical computing back in the 1940s and 1950s. The first electronic computers like ENIAC were enormous. They filled entire rooms, were incredibly expensive, and possessed capabilities that seem laughably limited by today's standards. We've come a long way since then with classical machines, and the journey for quantum computers will also be long and arduous. The biggest, most persistent technical monster that researchers battle daily is a phenomenon called decoherence. Qubits, those delicate carriers of quantum information, are incredibly sensitive. They are like divas of the subatomic world. The slightest vibration, a stray magnetic field from nearby equipment, even a tiny, almost imperceptible change in temperature can cause them to lose their precious quantum properties, their superposition and their entanglement. This loss is decoherence. It's like trying to keep thousands of spinning tops perfectly balanced on needle points in the middle of a hurricane. Scientists are working tirelessly on ingenious ways to shield qubits and develop robust quantum error correction. Then there's the sheer mind-boggling difficulty of actually building and precisely controlling large numbers of high-quality qubits. We don't just need a few, we need many, and they all need to be almost perfect. We need many high-quality qubits that can be reliably entangled with each other and manipulated with exquisite precision. Current quantum processors feature tens or perhaps a few hundreds of qubits. To solve truly world-changing problems, the kind that inspire these efforts, we'll likely need thousands, maybe even millions of stable, interconnected and controllable qubits. Scaling up the technology while maintaining qubit quality and coherence is a massive engineering feat. And of course, there's the unavoidable issue of cost. Quantum computers at this current stage of development are incredibly expensive to design, build, and operate. They require highly specialized laboratory environments, often involving ultra-low temperatures near absolute zero. They need exotic materials, incredibly precise lasers, and teams of highly skilled physicists, engineers, and computer scientists. This means that access to these pioneering machines is currently limited, primarily to major corporations, national research institutions, and well-funded government labs. Making quantum computing more accessible and affordable over time will be absolutely crucial for widespread adoption and for democratizing innovation. Section 9. Our quantum future: computing, the fabric of reality. So what does the future look like? A future increasingly influenced, perhaps even defined by the rise of quantum computing? It's a future filled with breathtaking, almost unimaginable possibilities. Imagine a world where new life-saving drugs and personalized medicines are designed and validated in days, not the decades it currently takes. Where hyper-efficient solar panels, designed at the quantum level, provide abundant clean energy for all humanity. Where we can accurately model the Earth's complex climate systems, allowing us to develop truly effective and timely solutions. This isn't some far-fetched utopian dream. It's a future that quantum computers could genuinely help us build. The impact will likely be gradual at first, then perhaps suddenly transformative in specific areas. We'll probably see specialized quantum computers or quantum processing units, QPUs, tackling very specific, well-suited problems first. Problems in materials science or drug discovery or financial modeling. Then perhaps we'll see more integrated hybrid systems. Systems where powerful quantum coprocessors work in concert with the fastest classical supercomputers, each tackling the parts of a problem they are best suited for. Eventually we might see more general-purpose, fault-tolerant quantum machines. The universe, after all, is quantum. Learning its language will unlock its secrets. This new era of computation will also inevitably reshape our workforce and our global economy. We'll need a new generation of quantum engineers, quantum algorithm designers, quantum software developers, and quantum physicists. Our educational systems, from universities down to high schools, will need to adapt to cultivate these new skills. Entire industries will need to transform to harness this new power. It's a significant societal shift, not merely a technological upgrade, but it's a shift that promises to empower us, to give us new, incredibly potent tools to understand and to shape our world for the better. The relentless human quest for quantum computing is about so much more than just building a better, faster calculator. It's a profound testament to our innate human curiosity, our unyielding drive to understand the universe and our unique place within its vast, intricate tapestry. These extraordinary machines, born from the deepest and most counterintuitive laws of physics, reflect our own remarkable capacity for wonder, for imagination, and for sheer ingenuity. The future, in many ways, is quantum. And it's not just passively arriving, we are actively, brilliantly creating it. One qubit, one algorithm, one stunning discovery at a time. The cosmos awaits.